For years, increasing the intelligence of foundation models required a rigid compromise: exponential increases in brute force parameter scaling and massive hardware expansion. Two recent model architectures, Qwen3.8-Flash-Next and GLM-5.3-Flash, diverge from this trajectory. They achieve massive gains in reasoning capabilities while radically shrinking their active compute footprint. Across mathematical derivation, high-order reasoning, and software engineering benchmarks, both models outperform previous 400 billion parameter flagships. They reach this output quality using roughly 1/9 the pre-training floating point operations of the previous generation. During live execution, these frontier models remarkably activate only 6 to 18 billion parameters for every single token. This reduction relies on software-hardware architectural co-design, bypassing the physical constraints of traditional GPU compute. We can trace this efficiency to 4 specific engineering pillars. First, hybrid token mixing. Second, multi-branch residuals. Third, advanced memory decoupling. And finally, orthogonal optimization. Architectural efficiency has become the deterministic factor in foundation model performance. Standard transformer models rely on self-attention, which carries a quadratic compute complexity. As the sequence length grows, the computational cost squares. When context windows stretch toward 1 million tokens, this quadratic scaling leads to severe serving memory bloat and massive prefill latency. Replacing attention entirely with pure linear recurrent mixers removes the compute bottleneck, but it often degrades precise multi-hop associative recall, the ability to accurately retrieve specific data across long sequences. Both Qwen and GLM architectures utilize an asymmetric 3-to-1 layer-wise hybrid token mixing ratio to resolve this. 75% of the network utilizes linear recurrence, specifically Qwen's gated delta-net and GLM's linear attention, to maintain a constant state accumulation. This linear mathematical formulation ensures that the step memory footprint never expands, allowing for constant time next token state transitions across arbitrary context lengths. The remaining 25% of the network consists of global sparse attention layers. These specific layers preserve exact routing for complex data retrieval. Qwen achieves this through a micro-block indexer. It evaluates relevance in blocks of 4 tokens, capping the attention compute budget at exactly 2048 tokens regardless of sequence length. GLM approaches this via dynamic sparse attention, which routes queries exclusively to high activation key neighborhoods across the sequence. Dedicating 75% of the layers to linear recurrence eliminates the prefill compute barrier, while the intermittent sparse attention layers maintain 1 million token recall. The second bottleneck occurs in network depth. When models scale beyond 40 layers, they suffer from representational attenuation. In standard pre-layer norm networks, the variance grows as depth increases. Early syntactic features are often divided by increasingly large variance denominators, causing them to be obscured by high-level reasoning abstractions. Qwen resolves this with a gated residual architecture, splitting the single residual stream into 4 independent, parallel branches. Sublayers read from these branches through data-dependent, low-rank bottleneck gating, which filters out signals that are irrelevant to the token's current context. After processing, the sublayers independently update the 4 branches using learned scalar weights. GLM employs manifold-constrained hyperconnections, projecting cross-layer connections onto geometric manifolds to suppress intermediate activation outliers. This architectural separation allows specific network branches to specialize. Some preserve low-level token syntax, while others develop high-order reasoning trajectories, preventing representational crosstalk. Multi-branch routing maintains stable gradient flow throughout ultra-deep networks, allowing models to preserve foundational syntax while executing logical abstractions. Scaling a model's parameters historically meant hitting the strict physical capacity limits of GPU high-bandwidth memory. These new architectures bypass this constraint through host DRAM offloading, moving immense parameter loads off the accelerator and into the host CPU system memory. During pre-training, Qwen stores 51.2 billion parameters of frequent n-gram embeddings entirely in the host CPU's DRAM.
When prompt tokens are hashed, an asynchronous direct memory access transfer streams these indexed embeddings across a PCIe Gen 5 connection into the GPU. This transfer time is hidden. Because the payloads are small relative to the bandwidth, the data arrives while the GPU computes its initial operations, resulting in zero execution delay. GLM utilizes a parallel memory decoupling strategy for deployment, relying on the K-Transformers execution framework. K-Transformers executes a 321 billion parameter model on a single consumer GPU by pinning the attention layer's NVIDIA RAM while running the sparse routing experts out of standard system RAM. Decoupling parameter capacity from GPU VRAM enables the deployment of 300 billion parameter models on single consumer-grade workstations. Training models of this scale introduces an algorithmic bottleneck. Standard first-order optimizers like AtomW struggle to process the highly varied matrix shapes found in mixture of expert layers. This mismatch produces unbalanced spectral gradients, which can cause training loss spikes. To prevent these crashes, researchers traditionally implement months-long batch-size warm-up schedules. The Qwen team addressed this by co-designing the network with Muon, a second-order matrix-based optimizer. Muon calculates its update direction by applying an 8-step iterative orthogonization to 2D linear weight momentum matrices. It then applies a dimension-invariant RMS scaling factor, which ensures that the magnitude of the update steps remains strictly uniform across matrices of any rectangular dimension. Muon is applied to specific geometric parameters, like linear projections and MoE expert transformations, while AtomW continues to handle discrete token embeddings and router logits. Segregating these optimizers allows for the elimination of batch-size warm-up. Training launches immediately at 4 million tokens per batch, utilizing a higher learning rate without causing gradient spikes. Co-designing the optimizer with the network architecture allows these models to reach convergence with roughly 1/9 the training flops of their predecessors. The Flash blueprint operates on 4 integrated vectors: hybrid token mixing, multi-branch residuals, memory decoupling, and orthogonal optimization. These 4 concepts combine to form a cohesive execution engine that definitively establishes a new baseline for the open weights industry. This chart displays the architecture's results on autonomous engineering benchmarks, including a 62.5% score on SWE Bench Pro and 63.4% on DeepSUI. These systems execute continuous, long-horizon coding workflows at a fraction of the traditional marginal compute cost. The technical trajectory verified in these releases informs the forthcoming generations, including Qwen4 and GLM-5.4. Ultimately, the Flash blueprint establishes integrated systems engineering as the definitive primary lever for advancing frontier artificial intelligence.